Kinsyn. In this film, a designer and a digital computer converse freely with one another. Not only in words, they draw pictures for each other. With graphical input devices, the designer can transmit spatial relationships to the computer. In response, the computer generates information and presents it graphically to the designer. The computer, in this case, is a relatively inexpensive machine as computers go. It is of a kind commonly found in medium-sized engineering firms. What is uncommon is the way in which this computer is being used. Computer facilities for Kinsyn were provided by the Mechanical Engineering Center for Computation and Analysis of the Massachusetts Institute of Technology. This is a schematic representation of a 4-bar linkage mechanism. It is being animated on a computer display screen. What is unusual about this particular linkage is that it was especially designed by means of the computer to produce the particular motion which you see. Design of a mechanism to produce a preconceived motion is the process of kinematic synthesis and is the main purpose of the Kinsyn computer system. I am Roger Kaufman. In this film, you will see the three of us, Walter Maurer, the computer, and me. Title music was composed and played by John Appleton. This looks like a pretty good mechanism. Here we have a fixed framework which represents the design for a guideway vehicle which is under development here at MIT in the mechanical engineering department. And the computer is moving this body with respect to that fixed reference framework. What you are witnessing is a computer program which is designed to kinematically synthesize mechanisms capable of moving a moving body through certain prescribed design positions or precision positions. In this case, this roller assembly is the body that we're trying to guide around, and the computer is moving it by means of a 4-bar linkage mechanism. Walt, why don't you go to a clear file and show us how you can sketch in design positions into the computer. You're undoubtedly familiar with linkages in various aspects of life. For instance, here I have a car hood linkage. The problem is, how do you design a mechanism of this type to produce a prescribed relative motion of one part with respect to the other? We have here a very small computer, an 8K IBM 1130 computer, which has been rigged up with certain specialized graphical input devices and a very low-cost display scope, so that with this simple, relatively modest hardware, we're able to interactively have a designer and the computer explore the properties of their design. This program differs from most programs in that when a designer sits down at the computer console, he doesn't know exactly what course he will follow in the design, but he has at his command a computer which has been essentially taught to be a very skilled assistant in this design process. The designer can sit down and essentially explain his kinematics problem to the computer, and the computer instantly understands what needs to be done to solve the problem as specified, If he doesn't like that solution, he can change his problem and interact with the computer in a sort of a dialogue. This flickering spot represents a directed line segment fastened to the moving body. And by means of this globe or graphical sketching device that we have connected up to our machine, the designer can manipulate its position around on the screen, just as though he were drafting. By means of these data switches, he specifies to the computer that he likes that as a design position. Let's take a look at how we could use this Kinsyn program, for instance, to design an orthotic brace for a person with a weak knee. By means of this program, a person could sketch in the actual positions that a normal leg would swing through in the process of motion of the leg. Here, obviously, Walt's just sketching in some random design positions. So we have a thoroughly disjointed leg. This is just to show how one can locate a moving body with respect to a fixed framework. But by means of this program, for example, a person could take X-ray data and either type it into the computer or sketch it in exactly against the coordinate frame and custom design a brace that would fit an individual patient. As you can see, this is a general purpose program. The program doesn't care whether it's designing knees or designing a vehicle or any problem of generating a prescribed relative motion of one body with respect to another can be solved using the aid of this Kinsyn system. In its current stage, this program can be used for any planar motion problem. For instance, for function generation, path generation, or motion generation by means of linkages or slider mechanisms. The program is based upon Burmester theory. It has many options the designer can choose either from the keyboard or by means of the data switches. Just for the fun of it, Walt is in the process of putting in some random disjointed design positions for a leg. Walt, why don't you show us the poles of rotation? For those design positions that Walt just happened to pick, the computer is now displaying some very useful design data. These are poles of rotation. As the body moved from one position to another, that motion could be accomplished by a simple rotation of the body about one of these poles. For instance, as the body goes from position 1 over to position 4, that motion could be accomplished by just rotating the body about this point P14. So these poles of rotation are poles corresponding to two positions of the moving body with respect to the fixed body. Walt, why don't you branch on and find some actual X-ray data for this problem? There are also image poles shown here, which are the positions that these poles take on in their reference or number one design position. So the problem in designing a knee joint is that there isn't a simple, single, fixed turning joint associated with all the positions that the knee bends through. But there's a combination of a sliding motion and a rotating motion that takes place in the joint. So this combination of rotation and sliding means that there's no single point about which the lower portion of the leg rotates as a person flexes his knee. What we'll show you is how, using this program, one can synthesize a linkage or a mechanism to guide one portion of the leg through exactly the motion that it would take on in a normal leg. These sketches were actually done with much more care than the one that we just did a moment ago. These are dimensionally accurate, and these positions were taken from actual X-ray data. So here you can see the relative motion of the femur and the tibia with respect to one another as the leg moves through 4 discrete positions. Now suppose one were to try to design a linkage to to swing the leg through these positions. For instance, some sort of an orthotic brace device, or perhaps in a prosthetic device, one might want to duplicate the exact motion encountered in the normal leg. In order to design a linkage, one would need to find certain points, fixed pivots, fastened to the upper portion or fastened to a framework attached to the upper portion of the leg, and moving pivots which would carry the lower portion with respect to the upper portion. The computer is now calculating curves which are the loci of these fixed and moving pivots. And one of these curves is attached to the fixed framework, in this case the femur, and the other curve is attached to the moving tibia. Here the computer is displaying the actual design positions that this leg takes on by means of this little directed line segment which is attached rigidly to the leg. These positions were taken off the X-ray data and were put in as the reference for the motion of the lower part of the leg with respect to the upper part. These curves are the loci of the fixed and moving pivots for the motion which we specified. These are design curves or synthesis curves, and this curve represents points which, for those 4 design positions, have the property of falling on a circle in each of the 4 positions. The other curve represents the centers of these circle points. And there are 2 symbols in the center here which represent possible sliders for a slider crank mechanism which would be capable of also guiding the body through those 4 specified design positions. For 4 specified design positions, there's infinite loci of possible circle points and possible center points. And these curves are different for each specified motion. It's important to recognize that this is a synthesis program. The input data here was not the design of the mechanism, and we weren't looking to see how the mechanism behaved. Instead, the input data here was the kind of performance that we required, the precision positions for this mechanism. And here we're showing at a larger scale these curves superimposed upon the X-ray data for the leg. Here's the femur, and here is the tibia in its different design positions. So, for instance, we now would like to know what are the possible fixed and moving pivots. How do these compare with one another? How do we match these up?
With this particular plot, we know that any point out here will not be one we want to look at because it will be off the sketch of the leg.
For instance, we could select the slider point and one of these other circle points. A slider can be considered as a point which in each of the design positions moves on a straight line. In other words, it is actually a point whose center of curvature falls at infinity. And we have here 2 kinds of slider points. One we call a concurrency point, the other a slider point. And these can be used for designing slider crank mechanisms of the different inversions, either turning block mechanisms, tumbling block mechanisms, or slider crank mechanisms. These differ from one another in that you hold one member fixed in one case and a different member fixed in another case. Here you see a bouncing spot which is showing the one-to-one correspondence between the circle points and the center points. By means of the data switches on the computer console, Walt is able to control the speed with which the spot bounces, and he can back it up, go forward, move it around to different parts of the file. It's bouncing between a circle point and the corresponding center point. It's bouncing between the 2 separate curves. And that really represents a possible link for a mechanism which would be capable of guiding the leg through these desired design positions. He just selected that as a possible link for the mechanism. The computer is now typing out on the console exactly the coordinates of the particular circle point, center point pair that he just selected. This bouncing spot up here represents a possible crank for a linkage that will guide these bodies through these various design positions. Furthermore, now that the designer has selected his first link for the mechanism to guide this body, as he selects his second link, the computer is flashing on this table down here at the bottom of the screen. Right now, the computer is flashing double crank. This means that were the designer to select this particular link that is represented by this bouncing spot up here, he would end up with a double crank mechanism, a linkage in which both of the members that are pivoted to the framework will be capable of continuous rotation. As he moves to certain other positions, the computer flashes double rocker mechanism, meaning that the links are only capable of rocking back and forth, but because of the geometric constraints imposed by the linkage, they can't have a complete rotation. In addition, whenever he stops the spot to study a particular choice or a particular potential choice of a linkage, the computer gives him some additional design information by flashing whether or not the linkage is acceptable, meaning that the linkage would be capable of moving the body through the specified design positions, whether the linkage would be capable of moving the body through the design positions, but would require guidance through certain collinearity positions when two links lined up with one another, for example, or whether the linkage would be unacceptable in the sense of being unable to be assembled in each of the design positions and move continuously between these positions. And in addition, the computer gives the designer information both on the screen and on the typewriter as to whether or not the mechanism will move through these various design positions in the order that the designer specified. Thus, there's a tremendous amount of information which is presented to a designer very graphically in the most natural form for him to understand the information that is presented. Normally, this information might be computed and printed out on a line printer, for instance, and then the designer would be faced with a table of numbers which would really have very little significance for him in the context of an actual design. Here, the designer is in a position to judge his mechanism in the context of the actual frame and body moving around, and he can interact with the computer in a graphical fashion by means of the sketching devices. He can change his various design positions. So it's a very natural way for a kinematician to interact with a computer. And even a relatively unskilled designer can come up with very good mechanism designs with the aid of this very sophisticated system. Well, why don't you pick the slider as the output link, and let's design a slider crank mechanism and see whether we can get a good one to move this body through these design positions. See, the problem here is that if you were to pick a single pivot to move the body, say, from the first position to the second position, you'd need to pick a different pivot. The pivot would have moved as you went from the second position to the third position, and it would have moved again as you went from the third to the fourth position. So what this linkage does is it accomplishes this change in the position of that pivot, or that pole of rotation between the design positions. Now we've selected a tentative linkage design. To do this by hand would have taken us many hours. On the computer, it's only taken us a matter of minutes. And furthermore, we might want to later on make some further changes in this thing. Having the computer program here, we can make these changes and pick out a new design in even less time than it has taken us to get this initial design. Now we'd like to see how does this linkage behave And how does this body behave as it moves through its design positions? In other words, we want to animate this linkage on the screen and judge its performance not at the precision positions. We already know that this particular linkage will move the body through those positions, but we want to see how does it behave in between these design positions.
First, we'll just show the leg. It is guided by the linkage, but we will study the linkage characteristics a little bit later. But let's just see if the leg is going to move through these positions as we were told before.
We've changed scale once again. We're looking at this at a very large scale so that we can see the entire leg moving around, and we'll be able to see whether the linkage does move it through the design positions in the right order. We already know it does because of the messages that the computer has told us, but this will be the proof of the pudding.
This is not the linkage moving right now. Right now we're just getting a reiteration of the design positions.
This was the input data that we started the problem with. Now the computer is showing how the mechanism moves the leg as it goes between the design positions. Okay, it started out in the first position, and now the computer is moving it in the direction of the second design position. This is not an approximate solution. It looks as though this move missed that second design position. That's not really true. We draw the mechanism in certain widely separated positions so as to avoid cluttering up the screen. We can move it back actually and show you that the leg does go through exactly that second position. Now it's headed up towards the final design position.
Maybe we ought to have just a blow-up of the knee joint to show what's happening in the area of the knee, which is our real area of interest.
Okay, let's let it go up to the, well, as you can see, it was heading right up through the fourth design position. At any point in the solution, we can get out a hard copy plot on the data plotter, and we can have a permanent record, or we could take a photograph of this. Here we're looking at the bottom part of the femur at a larger scale once again, and we'll show you the various design positions, and once again let's show them the leg moving through those positions.
First the design positions, the first, the second.
Well, why don't we put up the transmission angle? Another piece of useful information in designing a mechanism is how good are its force transmission properties. We can put a scale of the transmission angle for this particular linkage up on the screen, and it will tick mark a number which is an indicator as to how good a mechanism this would be. In addition, one can make a great number of judgments as to the dynamic properties of a mechanism by studying the time sequence of these positions. For instance, you can look at the spacing on the positions and decide what are the velocities and angular velocities of the mechanism or of the body as it moves through these design positions.
With this blow-up, one could, in between the design positions, see if there was any interference with the normal movement in this knee area. Let's go to the linkage and show that transmission angle.
This angle is a measure of the transmission between the input link and the output link. This is one of the many kinds of design information that a designer can get out. These were the specified precision positions, and here you see the linkage itself moving the body through those precision positions. To avoid cluttering the display, Walt isn't bothering with the display of the actual body moving along, but is just showing the links of the mechanism that is doing this actual driving. This is a slider crank mechanism. It's a very compact linkage so that it would be possible to design a leg brace that would be quite compact and would not take up too much space. As a result, it's it's kind of crowded in there on the display and a little bit difficult to see. But you can see over here the tick marks which indicate exactly what the transmission angle for this linkage is with the particular link that is driving.
Driving from the crank, you can tell this because of the equal increments of this crank going through here. It's marching along at equal increments and moving this coupler plane, which this line is in the coupler plane, and this, so the short line segment through the design positions.
If he wants, this program allows him to interchange and drive from the slider rather than from the crank. The slider's a little bit unclear in there because it's buried under all those lines. We could get out the design data on the line printer, or else we could get a hard copy on the plotter. The program will draw the linkage in its various design positions on the screen, and then it will go back and make a permanent record for our files. This record is exactly the same as the one that is over here on the screen, but is done with pen and ink. Kinsyn uses a computer, but this does not mean prefabricated solutions to mechanism design problems. On the contrary, Kinsyn enhances creativity. Kinsyn is like a knowledgeable associate with whom the mechanism designer can discuss numerous alternatives presented graphically and in context. In the process, he crystallizes and perfects his own thinking and progresses from a dimly conceived vision to a concrete and effective device. Kinsyn is versatile. It is a kind of jack of all trades. It can go from biomedical devices to transportation problems to machine design, and all without any change of programming. In this film, we have shown how Kinsyn is used in the synthesis of 4-bar linkage mechanisms and slider crank mechanisms. But Kinsyn also has provisions for studying a wide variety of other planar and spatial devices. The analysis of one such mechanism is about to appear on the screen. Kinsyn permits better solutions. For example, by being able to prescribe in advance the exact motion we want, we can synthesize a brace that will allow the knee to bend in a natural way without the pain and discomfort of a single pivot device.